Thank you very much for attending. So, as Murad said, I design multi-target tracking algorithm for a living, but more in a sort of a generic point of view. And quite recently, I turned to space. So, what I want to show today is my perception of the problems we have when you are tracking objects in space, and how I can relate that to my experience in more generic setting. All right, so first of all, I'm going to talk briefly about the context of multi-target tracking in space. And we'll see that we can sort of decouple it in a single target problem, tracking problem, and a multi-target tracking problem. So I will mainly talk about the single target tracking problem today. I might show you, if I have time, a video on how it works when you sort of embed it in the multi-target environment. So let's start. So first of all, what is space situational awareness? So I found two definitions online. So basically, in a nutshell, we want to know what's going on in space. We want to know about all the orbiting objects. So it could be man-made satellites, space debris. And we want to sort of maintain a chart of the skies, know where each of these objects are, and what they're going to do in the future. So you have a lot of commercial application, a lot of commercial activities that depend on military activities that depend on having an accurate chart of the sky. Okay, so these pictures, you might have seen them, just to scare people so that NASA can get funding. Like, we have a lot of junk in space, and we need to track it, because we don't know right now the number or the state, position, velocity of these objects. So you have a rough idea. We know that some orbits are more densely populated than others. So you have like the GEO orbit here, where you have a lot of communication satellites. And you have also a lot of LEO's objects close to the atmosphere. About the number of objects, no one really knows. So we know it's growing. That's the alarming factor. And we think, so I think NASA is trying to sort of estimate the number of objects that are more than 1 centimeter wide in space, and they end up with numbers around 16,000 or 20,000. And so if you look at the trend, the growing trend across time, then you see that we have sort of like, we had like 2 jumps recently. First of all, I think in 2005, an American satellite and a Russian satellite collided, so it produced a lot of debris. And accounted for the most part, so that's a major challenge. And more recently, I think the Chinese destroyed one of their satellites with a missile, and so it also produced debris. All right, so where can we help as trackers? So right now, objects in space, so NASA is maintaining a catalog, and every object is described by what they call TLEs, or two-line elements. So this is the space station. So I queried the website to get the information about the International Space Station. And the position of the object, position velocity, so its dynamical state, is given by what we call orbital elements. So you have 6 numbers here. And they inform you on the object's dynamical state, but it's a point estimate. We have no notion of uncertainty. So basically, right now, we can say it's probably here, but we don't know if we're sure of that information. Which is okay, but it's not enough, because we know that the sensing assets, so we are looking at these objects through radars, for example, or telescopes or cameras, are imperfect. So we know that we can't know exactly the position very accurately, so we want to be able to describe that uncertainty. So yeah, TLEs are not enough, for example, for situations where you want to assess the probability of collisions of two satellites. Right now what they do is they have 2 points, and if the 2 points are close enough, then some guy at the NASA receives an email and pick up his phone and call the owners of the satellite saying one of them needs to do something about it. But they can't have like a principled approach where they can assess probability of collision, since they have only points. And another issue right now is if you want people to coordinate their sensing assets, so telescopes from the UK, from the US, for example. They have difficulties because they don't speak the same language. They don't have a common representation of the sky, and without notion of uncertainty, it's very difficult to steer your sensor in the right direction. Okay, so the idea basically is to try to put a healthy dose of uncertainty with Bayesian estimation. And I don't know what healthy dose is right now. That's something that the community is still trying to figure out. All right, so first of all, I'm going to talk about the multi-object Bayesian estimation in a general context. So what are we trying to do here? So the idea is, when you want to approach a problem like that, we are going to try to describe everything probabilistically. And we are going to have a look at what we need to describe, all the sources of uncertainties in a problem like that. So first of all, assuming that that's a view on top of the sky, I want to track moving cars in a parking lot. Okay. So first of all, I need a way to describe the population of objects I'm interested in. So cars here. I might have to describe interactions between these objects. For example, if I know that objects are moving like in a convoy, then it's good to know because I can expect correlation between their motion model. I will have to describe how my sensor works. So assuming I have sort of a radar from the top that will give me a detection, so I'm going to get dots. Some targets might produce detections. Some may not, so we need to be able to describe misdetections also. False alarms or false positives, sometimes the sensors will tell us there is an object here, actually there is none, so we need to cope, we need to handle that uncertainty. A key element of multi-object tracking problems is that the number of objects is usually unknown and varies across time. So we need to be able to describe objects entering the scene. So in that case, new cars might come along the road and others might leave. All right, so this is not what we have access to. When we do tracking, we have access to whatever our sensor gives us, so for example, dots. So the question is, where are the targets? So basically, we can describe the problem in two separate levels. On the population level, we have two issues. How many targets are there? That is the cardinality problem. And which observation goes with which target? Because of course that's a known and we have to estimate that. And on the individual level, or the scale of one track, how do we predict the state of a target across time? How does my target move? And data update problem, which is a classic in the Bayesian frameworks, how do I correct the target state given an observation? So if we look at this generic setting in space, a few interesting things can be said. First of all, one of the disadvantages of these SSA, so space situational awareness setting, is that we have very few information of the objects we haven't seen yet. All right, they might come from a collision, but a collision that we did not observe, so we don't know how many and where these objects are. So we might have a new detection on a telescope, for example, and have no idea where this guy comes from. So that's a difficulty. The population is standard, of course, unknown and huge. That's, of course, a massive challenge for a tracking algorithms because we have to cope with a growing and very large number of objects. So, of course, we have computational issues. Now, on the other hand, we have one thing that goes, that helps us in space is the fact that the data association is what I would say moderately ambiguous in the sense that objects are reasonably far away, and so if you get a picture of a telescope or if you get returns from a radar, finding which observation goes with which target is still a challenge, but it's way easier than in a lot of ground surveillance tracking scenarios. For example, you have targets moving convoys, and you have smart targets trying to outsmart you. So, on the population level, the issues we have is how do we handle a population bigger than most, and how do we exploit the data association that is easier than most. So that should be, in my opinion, the two two aspects that should drive the relation of a filter adapted to space. All right, individual level. So I will more focus on that today. First of all, we have very limited sensor coverage, which means that compared to most the tracking problems, every target or every object in space is seen very infrequently, because we have a few telescopes and we have thousands of objects. So we might have to maintain some information about an orbiting object for days without having a single return from a radar or telescope to help us. The sensors used in SSA are very accurate usually. It's incredibly accurate. I don't know how they do that, but they have LiDARs, for example. They can produce observations that are good up to a centimeter. So it's great for tracking, of course, but it's also not so great for numerical stability, because we end up with very, very accurate observation models, very precise models. And so in a Bayesian setting, we might have numerical issues. On the other side, the dynamics are of course more constrained than in most problems, because orbiting objects are orbiting. So we have an idea of the way they're going to behave. So that's of course good for us. Now, what are the challenges then? How do we design a fast and accurate prediction model? Remember that the computational cost is important here, because we want to track a lot of objects. So how do we maintain some kind of uncertainty on the orbital model? This is still unknown. Another issue we have is that most of the sensors will not provide you one observation from, for example, a telescope. We give you no information about the range, the distance at which the target is, or the range rate. So one observation is not enough to have a complete description of the dynamical state. And finally, as I said, we have numerical issues. We have a large distribution with a large confidence region that we want to update with a very accurate observation. All right, so I will now focus on the single target tracking problem and show you a few leads that we are following in our team right now. So first of all, how do we usually do things? So when you want to model a target moving, this is one of the most famous and used models. I don't know if you guys are some experience in tracking, but the near constant velocity model is very common, quite convenient. So basically, it's in a 2D case here. We have the state is position velocity, and we're going to inject some noise on the acceleration and integrate that, and it allows us to have some kind of a natural model where the trajectories are random without doing crazy stuff. So it's quite useful for example, ground surveillance, where you don't expect your targets to move, change radically their bearing, or etc. So I'm going to show you on a video. So it's the same model. I'm going to start the same model with 4 different values of noise on acceleration. So if I have no noise, the object is now constant velocity, so moving on a straight line. And you can see that by adding level of noise, we end up having trajectories that are becoming more and more random, but still in a sort of natural way. And it's a very easy model to use, so it's very, very popular in target tracking. Okay, so can we use that in space? That's probably the first question that we should try to address. So the problem is if we take a Cartesian parameterization for the space, so I want to describe my objects in space with x, y, z, and x dot, y dot, z dot, I have a problem. Because of course, the orbiting motion model is not isotropic. I mean, I'm going to move along an orbit. So the NCD model is not adapted at all. I'm not going to show you simulations. I tried. It's ridiculous. I mean, the object goes, it's like a spaceship going, not orbiting, moving in a very, very random way. So it's not working. That's not the model that we can use in that problem. So the issue we have is actually the state space is not adapted. Cartesian coordinates are not great in space, are great to display results, but to analyze the motion model of an object, they are not. And luckily for us, The target tracking algorithms are not constrained to a state space, so we can use whatever the experts in space use and see if we can sort of integrate that in our trackers. So this is what I did. So now I'm trying to model my target dynamical behavior using the orbital elements. So that's the most common set of parameters used to describe a target in space. So basically, what we're trying to do here is describe an orbit, which makes a lot of sense. So you have 6 elements. So the longitude of the ascending node, capital or big omega, describes the plane of the orbit. So you have like a reference frame. Earth in the center, we have a reference frame, so this is pointing to Greenwich. And so omega will describe the plane of the orbit. The argument of periapsis will describe the orientation of the orbit in that plane. Then the semi major axis A will describe the shape or the size of the orbit. The eccentricity of the shape, if it's like squeezed or not. And finally, the mean anomaly M is an angle that describes where my object is right now on the orbit. So with these 6 parameters, I can describe any point in near Earth space. All right, so why are these orbital elements adapted? Because we can describe the dynamical model of an orbiting object in that frame. So the equations are like this. They are quite rough. But what we have here is how these elements vary across time based on, so A will be the perturbations, all the forces that perturb my orbit. So the way we describe an orbit, the orbit without perturbations, it's only the two-body problem that we can solve exactly. So we have Earth, our objects, and we assume that there's nothing else in space. We assume that Earth is a perfect, like a sphere, and we can solve that. And every time you want to add a physical effect, then you will change the orbit, and you will add a component to this to the perturbation vector. So assuming you can describe all the perturbation vector, all the forces with these vectors, then you have access to the dynamical model. Okay, this is super interesting, especially because if I assume that I have no perturbations, everything dies except this, I end up with a ridiculously easy system to solve. What I'm saying is that none of my parameters are changing, so my object stays on the stable orbit, and the only thing growing over time is the way where I am on the orbit. So basically, this angle grows and grows and grows. So it's interesting because in that frame, I can describe a orbital model quite easily. All right, so I'm going to show you a video about how it works on, for example, one geo orbit. Okay, so what you have here is I will generate an orbit without perturbations with that model, and I will compare it to an orbit that was numerically integrated and that includes most of the physical perturbation that we can model today. So you have the gravitational pull of the moon, of the sun, you have the solar radiation pressure, you have the drag, satellite drag, and you have other forces. One of them quite difficult to describe is the fact that Earth is not a sphere with a like a constant density. So if you want to describe the oceans, the continental mass, then it of course affects your orbital model. So here I'm just comparing the two of them, my naive model and I would say the ground truth. So velocity will be blue and position will be red. So I'm sorry, that's a bit confusing because the axis is blue here, but the red plot refers to position. So what we see here is that across time differences are growing, which is not surprising because assuming that my object is subject to no perturbations is not going to work in the real world. Okay, so you see, so every a unit is half an hour. So here we have roughly like 1 day. Okay, like 48 half hours, 24 hours. So you see that every day we have some kind of period in the error. Now if I do the same on a Leo, so it's an object much closer to Earth, I get also a similar, like a growing in the error at a different period. All right? But if you look at the scale, it's pretty scary because after a while, my objects, if I compare my predicted object and the real one, they are far away from hundreds of kilometers. So it's not going to work if I want to track the objects properly.
Sorry, what was the scale of the error in the previous one, the GO1?
A bit more. So it's in both cases you end up with a. Oh, here it's actually less on that scale. Here you have it's meters, so you have like 10 kilometers on this one, so it's like 60 kilometers. The geo model is somehow less. The perturbations play a lesser role than for a LEO model because when you are close to the atmosphere, you have a drag, satellite drag, and so when I am using my ideal model of perturbations, I'm neglecting the drag, and so the uncertainty is higher. So objects closer to Earth are more difficult to model. All right, so let's try to add some noise on our ideal model. So what we usually do when we do tracking is we add white Gaussian noise, as I showed you for an NCV model, for example. We have white Gaussian noise in the acceleration. So my idea here was to add Gaussian noise on the orbital elements. So if the thing is, we have to be careful here because the orbital model will be extremely sensitive to the noise. So here the values are of the order of -7 on eccentricity and order of -5 on the semi-major axis. So what I'm doing is I'm saying I know the plane of the orbit. I'm not going to change the plane, but I'm going to change a bit, squeeze the orbit a bit, and also change its size. So if I integrate over 5 days, you see that the orbit gradually shifts, and so I end up with something a bit thicker. So we have to be careful because if we play on other elements, so here I'm also changing the orientation of the orbit in the plane, so that's why, I get a larger error across time. And if I add errors quite randomly on orbital elements, I end up with nice pictures, but I hope no objects behave like this in space, and probably not. So bottom line is we need to be careful. The orbital elements are great to describe the base model, but now how to describe the noise, the process noise, we have to be careful. There's work to be done here. Okay. I'm going to talk quickly about another issue. Is can we initialize a track with a single sensor detection? Now, it's a fairly common problem in tracking. Our sensor does not cover the full dynamical state, so radars usually they have range, bearing, azimuth. They might have range rate, they have our Doppler, but we have no information on angular rates. Telescopes, on the other side, provide us with information on angles, possibly angular rates, with some pre-processing, but nothing on range or range rate. So the question is, assuming I get one observation, it's an object I've never seen so far, how do I initialize a distribution that describes my initial uncertainty on the state of the object? So the way it works here is that we're going to use an additional, we're going to use the physical characteristics of an orbit. That something we haven't exploited so far is that orbits, we're assuming the objects are in a closed orbit, so they have finite energy. And we have an energy equation that links all the position components to all the velocity components. So even if we get only an observation that covers 4 of the 6 components, then we can fill it up and produce a uncertainty region on the 2 parameters that we can't observe. So if you do that for a radar, with Doppler. So now the parameters you can't observe are angular rates. So you end up with the regions like that. So you're going to initialize the track saying, well, I'm going to try to fill this uniformly for my distribution, saying I have no idea. My target could go, so because it's angular rates, could go clockwise, anti-clockwise, I don't know. It's a bit nastier for the telescope. So here we have uncertainty on range and range rate. We might even have another region here. It's fairly unusual, but sometimes we do. So it's much more difficult to sample from that kind. But we have a solution at least. Okay, so how do we represent a probability distribution? Now that we know we have a way to describe, we have a sort of adapted state space. How do we describe uncertainty on the object? Okay, so again, we're going to look at what we usually do. So in sort of generic multi-target tracking algorithms, we either represent the probability distribution of a single object with a Gaussian mixture, or with a particle filter. None of them work great. First of all, the Gaussian mixture doesn't work really well because if you think about what should be the uncertainty in space, it's going to be some kind of a banana, right? Spread along the orbit, and it's quite nasty and difficult to represent with Gaussians. It's not adapted to Gaussians. Particle filters are nice, but the issue we have is that if we don't see an object for a while, the particle is going to grow, and we're going to have an issue when the object gets back into the field of view of a sensor, because, and if you have worked with particle filters, you know that, when you get a very accurate measurement and your particle cloud is spread, then if you compute the updated weight on each particle, each updated weight will be close to 0, and we're going to hit a numerical issue. So one approach that we have proposed is to try to get the best of the two worlds. So essentially maintain a particle distribution in the orbital elements, because it's nice and we can represent the uncertainty. And whenever we have to update the distribution with a new measurement, so the target was detected again by the sensor, then we're going to switch to a local frame where we can use a Gaussian distribution. So I'm going to show you on a picture. So assume that my, well, even Cartesian space, well, it's here in 2D because it's easy to see. My initial distribution is in blue, so I have this kind of banana shape, and green represents my local, the frame of my sensor. So first of all, what we do is we transform the distribution in the sensor frame. So in this case, polar coordinates based on my sensor, so like theta and range. Now the nice thing is that if you think about it, your sensor is on Earth. If you look at the distribution in your sensor polar frame or spherical frame in 3D, then the banana becomes something that is much nicer because we have uncertainty on range is the thickness of the banana, and the size of the banana will be uncertainty on angle. So we are going to approximate that distribution as a Gaussian approximation, as a Gaussian distribution. Now we are going to update that distribution based on our observation. In that space, because we're dealing with a Gaussian, we can use actually the Kalman filter. It works pretty well. So we can update our distributions, go from blue to red. And then we're going to sample the distribution and transport it back into our physical space. So you see now our red points represent the distribution after the update. So that works surprisingly well for the problems we have approached so far. It's not perfect because we are losing information here in the Gaussian approximation. So we are trying to work on other techniques. Okay, I'm going to show you an example tracking of one object. So what you're going to see here, so blue would be the orbit of the object, the trajectory. Red would be the period of times where the target is seen by a telescope. So we're going to see it twice. So first of all, here when the object is created, so that's going to be the initial determination, and then we're going to see it another time, and you will see how the particle cloud evolves. So if we get back at the beginning, here it's a telescope. So initial determination telescope, I have no information on range, so my initial distribution is like a ray, because I know that my target is not super close to Earth, I know it is not super far away either, so I just have a rough idea of like bounds on the range. And with the incoming measurements, we are going to be able to reduce it much more. So when the cloud is red, we are receiving observations, and when it's black, we are out of the field of view, so we are not getting any observations. So you'll see here that the cloud will start to grow quite quickly because we have no observations. And after one rotation, we're going to see the object again, and the cloud will reduce to a sort of more manageable size. Okay? All right. All right, how do we combine this with in the case of a radar? I'm going to show you a video, 3 videos to show you how fast we learn about an object when we see it, and how much we can learn from successive observations and not only one observation. So in that experiment, I am assuming I have a radar or a Doppler. So I have information about range, the 2 angles and range rate, nothing on angular velocities. And in that case, I'm going to see the object only once. So I have to rely on my initial, admissible region procedure to get an initial distribution. And what I'm going to plot here is the RMSE position velocity between the cloud of particles and the truth. So if I have access to only one measurement, then, well, my cloud grows very fast because one measurement is not enough. I don't even know if the object is going clockwise or anti-clockwise, and so you will see that some particles are spreading in both directions. And besides, I don't know exactly on which orbit I am, so you see here that each particle, the cloud spreads on different altitudes. Okay? And if you look at the error in position in blue, it grows quite fast. The velocity it decreases and then grows again. So here you see here, so you see particles moving the other way. So clearly,
so we have still the prediction phase.
So we have one observation, and then we rely only on prediction.
Okay.
We don't see the object at all.
This is prediction continued.
Yeah. My naive prediction. Okay. Now, I'm going to do the same experiment, but this time, following the initial observation, I'm going to assume that my radar sees the object 2 more times. And then, again, I shut the sensor off, and I rely on the prediction only. So if I move a bit, here you're going to see that the cloud of particles doesn't spread the same way, and it seems that it makes sense, 3 observations are enough to resolve the direction of the orbit. I don't have any particles rotating in the wrong side anymore. That's the uncertainty on position that grows very fast. Well, because my particle cloud spreads. But you see that, funny enough, each particle is on its own orbit, and some of them are on faster orbits. So we see that we have not yet pinpoint the state of the object, the orbit on which my object is. Now, if I do the same one, but now I assume I have 10 observations. So we see here, if you look at the errant velocity, that we learn a lot. It drops very fast because we have 10 following successive observations, and we learn a lot. And you see here that once, again, I shut off my sensor, if I rely on my prediction, I already have like a much smaller particle cloud. So after a while, we end up with something like this. So you see, it's not quite resolved yet. After so it's 50 seconds one time step. So after a few hours, I still have some uncertainty, especially on the size of the orbit. So we don't see it here, but these these particles are in the correct orbital plane, more or less. So I've estimated correctly the orbital plane, but I still don't know on which orbit the object is. So that's why I have these points correspond to orbits with a larger semi-major axis, and those who are shorter one. Okay. I will just finish quickly on the illustration of how all this machinery works when you embed it in a multi-target setting. I'm going to illustrate a tracking problem with the HISP filter, which is a new filter that we have also developed in the group. So essentially, the HISP filter is fairly adapted to the space problem because it relies on approximations that fit to the space problem. Namely, the HISP filter will assume that the delta station is moderately ambiguous. We'll make approximations that rely on that, and it's exactly the case in space. And it allows us to have a filter that's quite fast and is able to track individual orbiting objects while handling misdetections, false alarms, etc. So I'm going to show it on a scenario with 30 objects. So I assume I have like 3 sensors like that with 3 field of view. So the sensors are going to sweep along the latitude line. So each of them will see a few targets at any time, but most of the targets will at any time be outside the field of view of the sensors. So all right, so blue are the true objects. I'm sorry about the resolution, it's not great. Blue are the true trajectories. Green are real measurements. And red are false alarms. So no filtering here, it's just like the scenario. And you will see that we don't have a massive amount of false alarms, we still have some, so we need to resolve that. And we see the objects regularly, but we have a lot of blind zones. Most of the objects are on GEOs, but we also have nasty ones like that. That is on a highly eccentric orbit. It's more difficult to estimate the state of these guys. All right, so that's the result. I'm focusing now on one of the targets. So in these plots, so this is time. These regions are the regions when the target is in the field of view of one of the sensors. Okay, so most of the time the target lives on its own and we can't see it. First of all, if you look at the number of tracks, there will be the number of tracks that the filter maintains for that target. So obviously we would like this to be 1 all the time, meaning that we have correctly detected the target and we maintain 1 track. It's pretty good. So it's 0 at the beginning, and as soon as we see the targets the first time, we initiate a track and we keep it till the end. We have RMSE on position and velocity. So we see that following the first initial determination, we still had a rough idea where the object was, but we hadn't pinpointed yet the state of the object. So when the target left the field of view, the uncertainty grew a lot. Second time, we're able to correct our estimation, and then you always see this trend where it goes up, and then when you see the object, it goes down. And on velocity, we learn much faster, velocity of the object. For 2 of the objects, we had an issue where the filter produced 2 tracks at some point and decided to kill the old one. So that's fairly usual in multi-target filter, but it's not something that we want to see, but it happens. So basically, the track maintaining the target was not great, and the filter decided to create a new one and drop the old one. So we see here that at the beginning it was okay, but here we didn't see the object for a while, so the uncertainty grew, and at this point the filter said, okay, I'm off, so I'm going to start with a new track. So that's probably what is the most promising result for us, is that the computational cost, the runtime, is linear in the number of objects. So that's quite promising, because one of the biggest issues in space right now is that the filters they are using, I don't know if you have heard about the NHD, multi-hypothesis tracking filter, is very computationally expensive because of the combinatorics. When you receive measurements, you have to look at all the combination between the measurements and the tracks. It's really costly. And with that filter, that works on sort of clever approximations, that we are able to maintain an estimation of the orbiting objects in a linear time, with time linear with the number of objects. So that's fairly new. I presented this a month ago, and now we're working on coding this efficiently so that we can track hundreds of objects. Thank you very much.
This production is brought to you by the University of Edinburgh.